Hi, my name is Manish Gupta, and in this video, I'm going to talk about the LLaVA model, which is basically a visual instruction tuned model. So let's get started. LLaVA model has been really awesome at doing several interesting multimodal tasks, like supporting a multimodal chatbot. This is how the LLaVA model architecture looks like. If you really look at it, it is a very simple architecture. In a multimodal chatbot scenario, what you have is an image and you also have a user question coming in. So you take the image, you take the user question which has come in, also use some sort of language instructions to tell the chatbot that you must behave like a chatbot and so on, right? And then essentially, you process the image using a vision encoder. The text you basically pass as it is to the language model. And essentially, you have the image pass goes through a particular transformation so as to come so this is to map the image in the same embedding space or similar embedding space as the text. And then you pass these tokens, concat these tokens as input, pass them to Llama language model, Llama, right? And that basically gives you the overall overall model, which is basically called as LLaVA. Okay. Now this model is really good. As you can see using these examples. So if a user uploads this image and the user asks, what are the meals that I can cook with these? Now the model comes up with really nice and descriptive answer of this form, right? So with the variety of food items stored in the refrigerator, you can prepare several meals. For example, you can create a fruit salad, strawberries, blueberries, carrots, and so on and so forth, using these and so on and so forth, right? Now the user can continue the conversation. They can actually ask, I would like to do the fruit salad. Show me the recipe. And this is the awesomest recipe that you can see, right? I mean, which basically really uses the things that were there in the refrigerator and also suit the conversation that is going on. Okay. So this model, of course, there are more examples of multimodal chatbot scenario, right, where the model has been shown to be really useful. So given this image, the user can say, what are the things I should be cautious about when I visit here? So then, the model talks about various things, including sudden changes in weather. So there could be winds and storms, and it is very close to the water. So be careful not to be very close to the edge and so on and so forth, right? And then one can actually also ask a question, compose an engaging travel blog post about my trip to this place, highlighting the beautiful sceneries and so on. And here is a very nice blog. Okay. So LLaVA can do all of this. In fact, LLaVA model can also solve problems which require optical character recognition. So who will be interested in the contest in this image? And it's about CVPR, which is a very popular computer vision conference, right? And there's a nice description about who all will be interested in the conference, which is basically identified using this logo, right? In fact, it can also understand humor, can relate with the knowledge information as well. So, for example, do you know who drew this painting? Now, it can basically say that this is a very humorous situation about a dog being depicted with, where it appears wearing a woman's dress and so on. And then it can link that this looks very similar to Mona Lisa and therefore could have been basically drawn by Da Vinci. But then, well, this basically has a amusing visual turn to it. Okay. Now, the model can actually also do things. So LLaVA is also nice because it can also do things that GPT-4 kind of models, the multimodal GPT-4 could do. Right? So these are both examples from multimodal GPT-4 paper where there is humor in both of these examples. And here the question that is being asked is what is unusual about this image? Now, GPT-4 comes up with a short, crisp answer. The unusual thing about this image is the man is ironing clothes on an ironing board attached to the roof of a moving taxi. And the model the model comes up for this image. It comes up with an answer of this kind, which is practically pretty similar, right? If you think about it, it basically nicely tells about what is going on in this image. Similarly, if you look at this image, this is basically another humorous image where these chicken nuggets are sort of organized in a form that they roughly look like a map. So can you explain this meme or can you explain this meme in detail? You basically ask these questions and GPT-4 and LLaVA answers are pretty similar. Now, being similar, not a big deal, but what is the big deal? The big deal is that GPT-4, first of all, is not openly available. So you can only access it via an API. LLaVA is publicly available, right? And second, this model is GPT-4 is very large, very large, while LLaVA is much smaller, like a 13 billion parameter model. That's all, or a 7 billion parameter model. If you basically take the LLaVA model trained on the 7 billion llama model. Okay. So all of these are great things that you can do with LLaVA. So what is LLaVA? LLaVA is a multimodal instruction tuned model. How did they really create the LLaVA model? That's the question, right? So they created the LLaVA model by instruction tuning it using multimodal instruction following dataset. Now, of course, then the obvious question is, how do you create this multimodal instruction following dataset? Okay, so this is how they did that. They basically first used COCO images. So remember, MS COCO or the COCO dataset is an image captioning dataset. It basically has for every image a bunch of captions. So it basically has this input. So there's an image and there are 5 captions associated with the image. It also has like these bounding boxes associated with objects that are present in the image. So this is the input that is available in the COCO model, in the COCO dataset. Okay, but that's not enough to create an instruction following dataset. So therefore, what these guys did was to basically, take these COCO images along with captions and boxes, and then take that as input and prompt the GPT-4, prompt the text-only GPT-4 model so as to generate 3 kinds of responses: conversation, detailed description, and complex reasoning, which are going to be used for instruction following. Okay, so so the idea is that they created the instruction following dataset by taking the COCO dataset and then using the language only GPT-4 so as to create instruction fine tuning or instruction following dataset itself. Okay. The instruction following dataset basically contains 158K language image samples, of which 58K are conversations, 23K, these kinds of conversations, 23K are these kinds of detailed descriptions, and 77K are these kinds of complex reasoning question answers. Okay. So you see conversations. What are conversations? Well, they are multi-turn question answer pairs where the GPT-4 model generated both the question and the answer, both the question and the answer, while being conditional on the image, captions, and the boxes. Okay. Uh, the second kind of thing, I mean, of course, they use a prompt just to generate this, and you can actually look at the prompt in the paper, right? So that's that. Now, again, they also use GPT-4 to generate detailed description. So given this particular image, captions, and boxes, can you come up with a nice detailed description for it? Okay. And the third thing that they did was to basically use again, the image, captions, boxes, and prompt GPT-4 so as to generate some complex reasoning question, like what challenges do these people face? So, although the image is not visible here, the image is about a bunch of people just standing next to a vehicle and trying to see how they can put their luggage inside the black SUV vehicle. Okay. So that is what the challenge that they're facing. They're trying to figure out how to basically put their suitcases and backpacks in the luggage area. It looks like the group is larger than they expected to be put up inside the car, right? Inside the SUV. Okay. So that's that. So basically, in short, they take COCO images, they prompt GPT-4 so as to generate instruction fine-tuning data. And this is the data that they basically use so as to train the LLaVA model. Okay. So, and basically all of these 3 types of responses, which are used for instruction fine-tuning, are generated by GPT-4 using few-shot prompting. The specific prompts you can look up into the paper. Okay. Now that we have the instruction fine-tuning data and we know that we have to do multimodal instruction fine-tuning, how is the LLaVA model trained? Okay, so there's the same architecture as we saw earlier. The LLaVA model basically contains the language model, which is basically Llama itself, and that is why the name LLaVA. So basically, it's just a visual model in that senses. Okay. For images, they basically use a vision encoder. So that's basically our clip vision encoder, VITL14 encoder. And then for the text part, of course, they directly take the language instructions and whatever is the text, question and so on, and they encode it using the Llama itself, the Llama model itself. Now, of course, they also need to give instruction fine-tuning, so therefore they must give a system message also. In fact, their input looks like this. They have a system message and they have a specific stop token and then a new line, and then human says some instruction and then a delimiter, and then the assistant says some answer. Okay, human says some instruction, assistant says some answer. So in fact, the way the model is trained is basically on the next word prediction kind of loss, where this loss is actually computed only on the answer token. So the green tokens that you see, answer token and the delimiter, the stop token, only that is where the loss is computed. So if you look at the X system message, well, what is the system message? Is a system message. It's a chat between a curious human and an artificial intelligence assistant. The assistant gives helpful, detailed, and polite answers to the human's questions. Okay. Now, also, as input, you also provide human and X1 instruct. So basically, of course, if you have multiple question answer pairs, like you basically see here in the conversation, you have, the first one and then the answer to that, second question, answer to that, third question, answer to that. So you have multiple of them, and that is what you basically specify as part of the input here. Okay. Now, Of course, you compute the loss only over the answer token. So loss is computed over the answer tokens. But the X1 instruct, what is that? X1 instruct is basically X1Q and then the image. So X1Q is the first question and then the image, or it could be image and then the first question. So the order can be swapped randomly. And that's for the first turn. Now, of course, for the later turns, you don't want to give the image again, right? I mean, so essentially you just basically give the question. Okay, so for the first turn, of course, you have to give the image and the question as part of this X1 instruct. And then, of course, the answer goes there. But from the second question onwards, you don't really give the image, you basically just give the question. Okay, so that's that. That's how broadly it works. Now, the training is done in two parts. First is pre-training and second is fine-tuning, of course. So pre-training is done for feature alignment and alignment of the image and the language features. So in all cases, the vision encoder is kept frozen. So you don't really mess around with the vision encoder. You want to align the vision embeddings with the language embeddings, and therefore there is this projection matrix W that needs to be trained. Okay. So while doing pre-training, they actually filter the CC3 million dataset to some 595 image text pairs, and they pre-train using only the conversational data. So they take those image text pairs from CC3 million, 595K image text pairs. So of course these are actually different from these 158K, right? So essentially this is pre-training part, right? Which is basically meant to train this projection matrix nicely, So the pre-train using the conversational data, visual encoder and the LLM weights are frozen. So they don't, of course, mess around with the LLM weights, neither with the vision encoder. The goal is to basically learn this nice projection matrix W. Okay. They essentially train the model using these 595K image text pairs, and the loss is defined only over the answer tokens. Okay. Now, after the pre-training is done, so you basically have the vision encoder, you have the W, you have LLM, and so on. You fine-tune end-to-end. Again, you keep the visual encoder weights frozen, but then the LLM weights and the W, both of those weights are essentially updated. So you update both the pre-trained weights of the projection layer W, right, and also the LLM, which is basically indicated by F here, right, which is basically your LLaVA model. Okay. Now, fine-tuning can also, and for fine-tuning, they essentially make use of all the three data sets, the conversation data set, the detailed description data set, and the complex reasoning data set. Basically, all the 158K instruction following samples that they have obtained. Okay. That's basically for multimodal chatbot scenario. They also do experiments with the science question answering scenario, and their science question answering dataset, science QA dataset, already has a training part, which is basically what is used so as to fine tune the LLaVA model for science question answering. So now that we have seen how it is trained, let's see how does it perform. We already saw some examples of the performance in the beginning. And what they do here is to compare the performance of the LLaVA model on two interesting tasks, the multimodal chatbot and the science question answering task, which is also multimodal in nature. You have an image in context and you have a science question and you have to come with an answer. Okay. So they asked GPT-4 to come up with some scores so as to with some scoring for the outputs generated by the LLaVA model, right? While comparing it with GPT-4. So the question to GPT-4 itself is that, hey, if you look at this particular sample, and the answer that has been obtained for this sample, uh, would you prefer the LLaVA model output or would you prefer the GPT model output? Or rather, how much would you prefer the LLaVA model output versus the GPT-4 output, right? So now what you see here is that, on average, it was observed that that this LLaVA model performs 85.1 relative score compared to GPT-4. Of course, GPT-4 is better, no doubt about it. But if you really compare it with GPT-4, LLaVA model, while being so small a model, can give you as good as 85% of the GPT-4 performance, right? Of course, if you look at the three types of data sets that we had, conversational, detailed description, and complex reasoning, for complex reasoning, it performs really close to GPT-4, but for conversational and detailed description, it performs around average, so about 85%. Okay. Now, this is when you use the full instruction tuning data. If you did no instruction tuning, the performance is dismal. So as you see, the performance is about 4x smaller if you did not do any instruction tuning. So therefore, it is super important to do this instruction tuning using the multimodal instruction tuning dataset that they created by considering the COCO images along with some sort of teacher training from GPT-4. Okay. So that's that. Now, of course, they also tried to experiment with using part of the instruction tuning dataset that they created. So for example, what happens if you just use conversational dataset only if you use the detailed plus complex dataset or use some part of those and so on. Okay. But they observe that you get the best results when you use the full instruction tuning dataset that has been created. Okay. Also on Science QA, now on Science QA, they basically first report, they report the accuracy values using the state-of-the-art model, so the previous model. So the previous state-of-the-art model has been this multimodal chain of thought large model, right? And the GPT-4 also sort of performs so-so on the Science QA data set. Okay, but if you really look at the LLaVA model by itself actually performs almost close to the state-of-the-art. Now, if you combine LLaVA model with GPT-4, right, as a complement, so in the sense that you first ask a GPT-4 model, if GPT-4 is very confident about its answer, great. Otherwise, you basically say, otherwise you essentially, or if GPT-4 crashes, sometimes GPT-4 crashes saying, hey, I cannot come up with an answer, then you backfill the results with LLaVA. And you observe that the results are not very much better, right? But then they also used LLaVA plus GPT-4 as a judge. So what they do is to ask GPT-4 come up with an answer, ask LLaVA come up with an answer, and then they tell GPT-4, hey, given these two answers, come up with the best answer. And it turns out, in that case, this kind of an ensemble gives really better results compared to the state of the art, establishing a new state of the art with about 92.53% accuracy, right? So all in all, on both the tasks, multimodal chatbot task and also on science question answering task, LLaVA seems to perform really well. So in summary, what is LLaVA? LLaVA is a visual instruction tuning model using language only GPT-4. So visual instruction tuning dataset has been created using language only GPT-4. And they also contribute an automated pipeline to create language image instruction following data. They also contribute LLaVA, which is a multimodal model to follow human intent to complete visual tasks. Specifically, they focused on science question answering and multimodal chatbot as tasks. They have a multimodal chatbot demo running online, so basically feel free to go there and check out their demo right there. Okay. Their experiment showed that they could they could establish a new state of the art on science QA data set, and actually some examples really show excellent visual chat experience on the multimodal chat data. Okay, so that's it for this video. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my search on my homepage. Thank you.